So welcome to part 4 of DC to AC power inverter basics. This is a new type of transformer that you can use. You of course may remember in the previous videos we had this transformer here, which has a 12 volt winding there and a 230 volts winding there. Now I have a different transformer, and if you see, this one has the 230 volts winding up here, and it has a 9 volt winding there, and it also has an additional 9 volt winding there. So this is a so-called center tapped transformer. And I've also changed my circuit. Instead of using the amount of MOSFETs that I was using previously, which were 4 MOSFET, I was able to reduce them to 2 MOSFETs, which not only saves money, it also, unlike this full bridge that you saw, it also helps you to get more efficiency, because if you have a look at the full bridge, you have the resistance from this feed, or this and this. So both resistors add up and give you a power loss. But on the other circuit, you have only one transistor or MOSFET for each coil. There's L2 and L1. And what happens is, the oscillator with the 50% duty cycle now switches either this MOSFET or this MOSFET. And this is the special device, is the transformer. So if this coil, for example, if this coil is connected, you get a magnetic field that is polarized like clockwise. Okay? Then this coil is turned off, and suddenly this coil is turned on, and you get a magnetic field in the opposite direction. And what you get is a varying magnetic field, alternating magnetic field. And guess what? This coil picks up the alternating magnetic field and generates AC voltage from this alternating magnetic field. As on the full bridge, you also have to ensure that you have a 50% switch or duty cycle, because if you are going away from that, I will demonstrate that, what happens. I think you can hear the transformer since it's quite noisy. So watch the power consumption. This is without any load. So now it's well tuned, 50-50. Now I go like 30-70. So you can see the current is increasing. And what also happens is that one of the MOSFETs will get very hot, meanwhile the other stays cold. But if you got them on 50-50, both will heat up equally. So since the inverter is already running, you can see it's putting out around 225 volts. And now I connect my light bulb. And of course we get a voltage drop again, around 210 volts or so. I don't know, have I described it in the previous video, since I'm making these videos kind of randomly. The point with these transformers is that the voltage that is written on them, in this case 9 volt, is the voltage if you use 5 amps, which the transformer can deliver. The empty run voltage is much higher, so I would have to increase the voltage to like 12 volts to get out the power wanted. Well, in this case with this light bulb, I think you can do it like 10 volts and then it will be fine. But just let's try it. So I'll now increase the voltage until we get 230. So there we are, 230 volts. And this light bulb is just as bright as it is on the mains. So, but the problem is, if I disconnect the light bulb, the needle would go over the scale. So you also need, just like on this transformer, you need the control or regulation, voltage regulation circuit that you can obviously see here. I've shown it in the previous video. It's the voltage regulation system. This one can also be connected to this transformer. And there's another thing about these transformers, these that look like a block. They even are called block, and is this the manufacturer? I guess that's the manufacturer. Anyway, this transformer also has these issues. They are producing high voltage. Even if you get them the right way, if you get them in the right way and you get the 50% duty cycles, some of them are producing really weak spikes that go up, I think, to 1 kilovolt. They are really weak. I mean, you know these, if you have these lighters and they are empty and you can't refill them, and you have one of these electric with this clicking switch, you can take out the piezo crystal and then you have a small high voltage device. So I think the current of this 1 kilovolt spike is around as weak as one of these small piezo lighter high voltage devices. It's really weak, so it doesn't harm the electrical devices. But what it does is it will produce a small spark, and the spark will take the big current and big 230 volts and much current and will travel over the small spark gap. That happened to me in one of a meter, not this meter. It was a cheap digital meter, and I heard a bzzzt noise from inside the meter, and it even lit through the case, and well, then it smelled really bad, and the meter was broken. So there's a simple solution. You take one of these foil capacitors. This one's a 0.47 microfarads, 275 volts. I think I used these in my ZVS circuit that I rebuilt, and you just connect them in parallel to the output. That will give you a small disadvantage because the voltage pretty much stays the same if there's a load, but as you can see, the current has increased. I'm not sure if I have shown it before. Before it was 2. Let's put it away. So now we have 3 amps, and now we have 2.68. So the capacitor is eating quite some current, but therefore it's eliminating the high voltage spikes. And I think it's also smoothing out the signal a little bit. Okay, that's pretty much about these transformers with center tapped coils. So they are generating an alternating magnetic field in the core with these 2 coils, which then gets turned back into an electric current and voltage by the original primary or 230 volts winding. Okay, that was part 4 of basics building DC-AC power inverters.